Right, so the very first question, this was an achieved question. So if you see a U next to your page like that, then that's an achieved. We have to write U over V. So 10, wow, nice. Can everyone see okay? Yeah. Okay, good. So 10 cis pi over 3 over 4 cis pi over 12. Now, the rule for doing these is that you have to go 10 divided by 4 cis, and you can subtract the angles. Right, pi over 3 minus pi over 12 is pi over 4. So that's going to be 10 over 4 or 2.5 cis pi over 4. Right, that was the answer for that one. Any questions on that? Okay, this next question. We have to show that 3 plus I is a solution of this quadratic here. The best way to show that is to try and implement the factor theorem, which pretty much just means if that's x, then put it in everywhere you see an x in the equation. So that's going to be 3 plus I squared minus 6, 3 plus I, plus 10, and if that gives you 0, then you've got no remainder, so it's a factor. Right, so that's going to give us 9 plus 6I minus 1 minus 18 minus 6I plus 10, and that cancels. These two add to 19, these two add to negative 19, so they all cancel out. So 0, that equals 0, and that proves that we've got no remainder, so it must be a factor. Right. If you got those two right, then you got a mark of A3. 2 U's is equivalent to an A3 mark. Right, we'll do question 2, the first 2 parts of question 2 now. Okay, there's pretty much 2 ways of doing this. When you do a conjugate with a complex number, which bit changes its sign? The real part or the imaginary part? No. So the conjugate of 3 plus 2i is 3 minus 2i. It's the imaginary part that changes its sign. We're effectively going to do a conjugate here, except it won't matter which part you change. So I'm going to change, I did it by changing the sign in front of the root. The answer sheet does it by changing the sign in front of the 1. It wouldn't affect your answer. So I'm going to multiply everything, top and bottom, by root 3 plus 1 over root 3 plus 1, because that bit there is just 1. And in doing this, you should get rid of your root sign. So that's equal to 3 times 3 plus 3 root 3 minus 5 root 3 minus 5. Yep. No, go back. So, over root 3 squared, so that's 3 minus 1. Okay. So that's 9 minus 5 minus 2 root 3 over 2, which is equal to 2 minus root 3. There you have it in the same form there. A plus B root C. A plus B is just -1 root C. Questions about that one? Okay. So this next question, we have to find a complex number z so that this equation is true. So we denote our complex number is x plus iy. So 8 minus 2i, and instead of writing z, I'll do x plus iy. Any chance you could stop that? What are you playing with anyway? Yeah. Well, stop playing with. I don't want to say it. What was it doing? 8x. 8x minus 8x squared plus 8iy minus 2x I. That's bad order, but
where's 8x squared from?
I don't know. I don't know where I got that from. I lost my train of thought. I looked at the answer I wrote down before. 8x first outside 8iy minus 2xi minus 2i squared y, good, equals 8x plus 10i. So I squared is -1, so it's going to be 8x plus 2y plus I times 8y minus 2x. So the real part of this equation is 8x plus 2y. The imaginary part is 8y minus 2x. So what we need to do now is compare the real parts of the equations. So this side has 8x plus 2y, and it has to be equal to the 8x because it's the real part that we're comparing it to. So if 8x plus 2y has to equal 8x, then y has to be 0. Right, if y is equal to 0, then I times 8y minus 2x equals 10i. That's the imaginary part. So 8y minus 2x has to equal 10. Y is equal to 0. So negative 2x equals 10. X has to equal negative 5. Okay, x is equal to negative 5, y is equal to 0. X is the real part, so z, the imaginary number, is just equal to negative 5. Check if I got that right. Yeah. Okay, so let's do the achieved questions from question 3 now. Any questions on that before we move on? All right, everyone's looking thrilled. Show that the conjugate of u times the conjugate of v is equal to the conjugate of u times v. Right. So the conjugate of u 3 minus 2i. Remember, you changed the sign for the imaginary part. The conjugate of v is negative 3i because it's only imaginary, so you change the sign of that. Okay, so conjugate of u times the conjugate of v, if you expand it out, works out, and you take the I squared to be negative 1, works out to be negative 6 for the real part, negative 9 for the imaginary part. Now do the same thing by multiplying u and v first, then taking the conjugate of the answer. Right, I squared is negative 1, so that's 9i minus 6. And now if I take the conjugate of that whole thing, I change the sign of the imaginary part, so it's going to be negative 9i minus 6, and we've shown that they're equal, and that's what we're asked to do. Questions on that one? Alright. The last achieved question is showing that this is a factor. That's just the same thing as we did before. There's no imaginary part to this question. All you have to do is plug in, if you've got x minus 2 as a factor, then x has to be 2. Because remember, from solving quadratics or cubics factorized like this, the x is the opposite value of what's in the bracket to make it equal to 0 if it's a factor. Then all I have to do is substitute in x is equal to 2. So it'll give me 2 times 2 cubed plus 3 times 2 squared minus 11 times 2 minus 6. That should be equal to 0. That's 16 plus 12 minus 22 minus 6. That does equal 0. So we've shown that it's a factor. Okay, that was the last achieved question. You can still get an achieved mark for the merit questions, but we'll come to that in a sec. Any questions about those? Alright, let's try and do this one here. Question 1C, the first merit question. Alright, if I want to write 27i as a complex number in polar form, the angle, what's the angle of a purely imaginary number? So remember, if this is your complex number plane, you always start measuring from there. Here's the imaginary axis just there. So the angle has to be pi over 2, 90 degrees. So a positive imaginary number, the angle is pi over 2. If you want to get more than one answer for this, you're going to have to remember that the angle is pi over 2, or it's pi over 2 plus 2 pi, or it's pi over 2 plus 4 pi, because you can go all the way around and get back to the same point on the imaginary number plane, complex number plane. So the answer to this, z3, z to the power of 3, as a complex number in polar form, is 27 cis pi over 2 plus 2n pi. Any integer value of n will represent once more around the circle, an extra 360 degrees. Okay, so using de Moivre's theorem, z is then equal to the third root of 27, which is 3, cis, and we'll take n is equal to be 0 first of all to get our first answer. So it's going to be pi over 2, and de Moivre's theorem says that we can just, if we're taking the third root, we can just divide the angle by 3. So that divided by 3. So the first answer for z is going to be equal to 3 cis pi over 6. Right. The next answer, all we'll do is we'll take the second answer to be equal to the third root of 27 cis pi over 2 plus 2 pi. So n is equal to 1 now. And we'll divide that whole thing by 3 because de Moivre's theorem says that we can just divide the angle. So that's equal to 3 cis pi over 6 plus 2 pi over 3. Thank you. Which simplifies to 3 cis there you go. I didn't cheat at all. There you go. The last answer is 3 cis pi over 2 plus 4 pi, so 2 times around the circle more, 3 cis that should be a 6. Okay. Makes sense. I think that makes sense. I think the answer's right. Any questions? Is the answer perhaps wrong? Okay. Well, that's the first merit question. If you got that right, if you got one merit question right, then you got M5, so 5 points. Okay. Yes. This bit here? Oh no. That there? Sorry guys, that's not going to be heard on the recording if you're talking.
So how do you know that N1 and N0 are all
Tony. Well, we know that there'll be 3 solutions because we're finding the third root, and n0, 1, 2, 3 don't have to be the 3 answers. You could take n equals to 84, 85 and 86 as long as you get 3 consecutive ones, because if I took n is equal to 4, then it would just give me back the same result for n equals to 0. So any 3 consecutive numbers will work for that. Okay, does that answer your question?
Yeah.
Right, so z minus 3 plus 2i. So x plus iy minus 3 minus 2i. If I expand out that bracket there with the minus sign. So that's going to give me x minus 3 plus I times y minus 2. Lame. Right. And that circle is going to have a radius of 5, but the locus isn't just equal to 5, it's less than or equal to, so it's going to be the points inside that circle as well. Where's the circle going to be centered? It's going to be centered at the circle is going to be centered at that. X is going to be 3. Y is going to be 2. So there's the center of your circle. It has radius of 5. Then you draw a really nice circle. Okay, so the locus is the set of points which include this circle and every point inside it because of that less than 5. But the other constraint is that the angle has to be between 0 and 90 degrees. So the angle has to be between here and there. So your locus is all those points there. Okay, if you just drew me the circle, you got an achieve mark for that. If you did the whole thing, then you got a merit. So if you figured out the circle bit and drew the circle in the right place, that was still worth an achieved. Right, so if you manage to use this to figure out what the circle should look like, the equation for the circle, and then draw the circle, that's a U. It's adding these points on, that gives you a merit.
Why did you say this?
Because the circle isn't actually the locus, it's the circle equals to 5 and any point where the modulus is less than 5, so it's equal to or less than 5. Right? So that would be any point in the circle, but the other constraint was that the angle had to be between 0 and pi over 2.
Oh, okay.
See the points that fit into both of those.
Yeah.
Okay?
Oh, so it's like the 90 degrees.
Yeah.
Okay, so.
Okay, so before I answer this question, to get a U, you just had to get rid of all the square root signs. So I'm going to square both sides to get rid of this square root sign. It's going to give me x plus k equals all of that squared, which is equal to k squared minus 2k root x plus x.
Do you achieve for that?
No, you have to get rid of the square root sign still. Okay, so right, here's how I did it then, since this x will cancel off of that x. Now, all I've done is rearrange it, so I've got my square root on the other. Now I'm going to square both sides. It's going to give me 4k squared x equals k to the power 4 minus 2k to the power of 3 plus k squared. Then I can divide the whole thing by 4k squared, which will give me k to the power of 2 minus 2k plus 1 over 4. And the answer schedule said you had to go one step further, but I gave you the mark if you got to here, because I don't think putting this into brackets was really necessary. Right, so there's x in terms of k. questions on that one?
Could you
Yep.
just repeat that last part?
This part just here or the bit above it?
We square.
That bit there?
Yeah, yeah.
Right. So to get from here, you're all good with this bit's here? Yep. Right, so to get from here to here, all I did was I rearranged. So once I squared this, I put the 2k root x over that side, and I brought that k across. Yep. And then here I squared everything. So if I square one term, I just need to square every term. But if I square this, then it's going to be that. Which will go to this. And then I just divided through by 4k squared. K to the power 4 divided by k to the power of 2 is k to the power of 2. K to the power of 3 divided by k to the power of 2 is k to the power of 1. K squared divided by k squared is 1. And then divided by 4. Okay, and then I just put them into brackets. Okay, question 3, part D. Oh, what question? Did I mean to say question 3? Are we in question 2 still? C.
Oh, yeah.
2D. 2D, that's what I meant. Right, so we have to find values of n for which z to the power of n is purely imaginary. We've already covered this. Purely imaginary means the angle of the complex number in polar form has to be equal to what? If we've got a complex number and it's purely imaginary, what does this angle have to be? Yep, someone said it, pi over 2. Pi over 2. Or, what else? Here's the imaginary axis there. How far do I have to go to get this to a purely imaginary number? Pi over 2. There you go. That's purely imaginary as well. This point here, that's the just negative part. So the angle has to be pi over 2 or 3 pi over 2. You're right. Okay, so this complex number we've got at the moment is z is equal to, the modulus is going to be 2. I'll show that, I better show that. So it's going to be the square root of root 3 squared plus 1 squared. So that's the imaginary part and the real part squared added together, square root. So it's going to be the square root of 4, which is 2. So the modulus is 2. If you have your special triangle on your formula sheet, which you had, then you could see that the angle would be pi over 6, I think. Pi over 6. So that's just straight from the formula sheet by doing inverse tan of the imaginary part over the real part. I hope this is recording. Right. So we're trying to find values of n such that z to the power of n equals 2 to the power of n cis n times pi over 6. Because remember, when you raise something to the power, all you have to do is multiply the angle by that power. Right. Now we want pi over 2. So what value of n do I need to make that pi over 2? 3? Yep, so if n is equal to 3, then we're going to have pi over 2, because 3 pi over 6 is pi over 2. What about if we wanted to have 3 pi over 2? What value of n would we need then? 3 over 2. What's an equivalent fraction for 3 over 2 with 6 on the bottom? So if n equals 9, that would work as well. Do you have a question about? Luke, you look a bit, are you all good? Yeah, okay. Right, so we can go round another pi over 2 again. So pi over 2 is going to be another pi degrees, and we'll get back there. So all we're going to got by now is, so we found that one, then we found this one. So to go round again, it's going to be another pi, then another pi, then another pi, then another pi, not going out of course. So if n equals 15, that's another 6 pi over 6, which is pi, and so on. So the values of n are 3, 9, 15, and that pattern just continues. So 6n minus 3, I should say x, n equals 4 integer values of x. So starting at 3 and then going up by 6. Right. If you showed me one of these values, if you found the first value, that's an achieved. If you found all of them or found the pattern, if you found like 3, I think it was, then we saw you had the pattern, so that would have been a merit mark there. Right, find the modulus of this number z. So if you can find z by itself, just find z, then you get an achieve mark. So that's z is equal to 2 over 3 times negative 1 plus 2i plus I, which is equal to 2 over negative 3 plus 6i plus I. And then we're going to multiply this by the complex conjugate again. So negative 3 minus 6i over negative 3 minus 6i. This is so that you can get it as a purely real denominator, which, if you multiply these two together, it's going to give you I'll do it all. There you go. Sorry about that. My mistake. Okay, sorry, nearly there. Negative 6 over 45. Minus 12 plus 45. So if I make this 45 over 45i, then that's my z there. So to find the modulus, it's going to be 6 over 45 squared plus 33 over 45 squared square root of that. And once again, if you got to there, if you got to this point here, then I gave you the mark, even though the marking schedule asks for the number 0.745. So let's just type in your calculator. So if you found z like this, then you got achieved, and if you found the modulus, you got merit mark. Okay, so for this question here, you have to find 3 different powers of this complex number here. I'll write that in polar form, so that's going to be 1 squared plus 1 squared square root, which is equal to root 2. So our number z is going to be equal to root 2 cis. Now if the imaginary part is 1 and the real part is 1, then that looks like that there. So the angle is going to be 45 degrees, or pi over 4. Once again, that should be on the special triangles on your formula sheet. So that's z. So z to the power of n is equal to root 2 to the power of n cis n pi over 4. Okay, so that's what you have to draw on this page. So if I take z to the power of 1 is equal to root 2 cis pi over 4. Pi over 4 is 90 degrees. Root 2 is just there. So that's my first value there. So that's z to the power of 1. Z to the power of 2 is root 2 squared, which is 2. And the angle is going to be 2 pi over 4, which is pi over 2, which is 90 degrees. So there's that there is z to the power of 2. And z to the power of 3 is going to be 3 pi over root 4, which is this angle here. And the length of it's going to be root 2 times 2. So it's going to be twice as long as this one. So it's going to go out to just there. And that's your z to the power of 3 just there. So that's your 3 complex numbers, which are the 3 powers of z. Right, that's the last merit question. If you got 2 merit questions right, then you got M6, and 3 of those is M18. That is 18, and you had to get 19 for an excellence. So I think you had to get 1 excellence mark to get an excellence overall.